Hello, everyone, and welcome to another wonderful day of chemistry. So today, now that we've got a basic understanding of electron configurations and Aufbau, let's go ahead and apply it to a little bit more nuanced scenarios where the rules start kind of fraying at the edge a little. So in general, when we're trying to find the electron configuration from most of our species, we tend to look at our energetic levels and fill from low to high. And this works out pretty well, and this gives us our classic filling patterns. However, sometimes some irregularities start showing up, and it turns out most of these come from what are called our D-block elements. So these are going to be the elements where we start having our valence electrons in the D shell. So these are most commonly known as transition metals, because these represent groups, the elements in groups 3b to 11b. They are essentially going, or 3b to 12b. These are kind of our fun guys. And in general, one of the reasons why these guys are going to be slightly problematic is that you'll notice that the 4s and the 3d shell, and similarly 5s and 4d and 6s and 5d, their energy levels are really close, so some antics can show up. However, for the most time, we're going to tend to fill our S shell and then our D shell, because the S is just a teeny tiny bit lower. So for example, if I've got iron, this is an element, this is in group 8b. And 8b means I've got 8 electrons, 8 valence electrons. So I'm going to go ahead and start in my previous noble gas configuration, in this case argon, and then I'm going to put 2 electrons in my s orbital and 6 electrons in my d. So I'd have argon 4s2, 3d6. And this is going to work for most elements. However, there's 2 very notable exceptions to this trend. The first of these is what's called group 11b, also known as the coinage metals, because copper, silver, and gold, these were your traditional types of coins. So in these cases, we've got 11 valence electrons. So if I was going to follow the same rules before, I'd go ahead and I'd put 2 of these electrons in my s orbital and then 9 in the d. However, it turns out since these electrons are so close in energy, we get a nice energy boost by filling out the bigger subshell. So it turns out energetically, it's more favorable to have a complete D subshell than an S subshell. Most of the time, this discrepancy wouldn't make a big difference, except the energy of that s orbital is so close to the d that little difference in between these pairing energies makes a big enough difference to cause the system to form an S1D10 configuration instead of S2D9. So a good way to think about this is if there's any possible way to fill up a D subshell just by stealing a single electron from the S, you're gonna do it, because it's going to be a lot easier to pull that electron from that s orbital. Now, there's a very similar, essentially, little brother to this, and those are the group 6b elements. So this is going to be chromium, molybdenum, and tungsten. These often have some fun activities and will show up in a fair bit of interesting chemistry. However, for our purposes, what we're really going to be looking at is their electron configuration. So we've got 6 valence electrons in this case, which means we'd expect this to form S2D4. But note, all I would need is 1 more electron to have a half full shell. Then all of these electrons would all stay out of each other's way. However, when you have that little gap, everybody can move around a little bit much and they get in each other's way. So to keep everybody separated, we can steal 1 electron from that s orbital and move it up into the d. Again, this is only possible because of how similar those s and d orbital energies are. So as a result, we can form an S1D5. So again, we can expand this on our previous rule, but because the s and d orbital energies are so low, if you can form a full or half full D shell by stealing a single electron, do it. And this is going to be the reason why you can follow your general electron filling trends, except for any 6B or 11B elements. So again, chromium, molybdenum, tungsten, copper, silver, gold. One of the best ways to figure out when you're going to move an electron over is to actually draw out the full arrow configuration. However, there's some other important things where we need to bring into mind how these electron configurations work. And one of the other important ones looking at is ionic species, because it turns out not all elements have a neutral configuration. So if I want to find the electron configuration for an ionic species, it's often easiest if you start with the electron configuration for the neutral species and then figure out how you need to modify it. So for example, if I've got a cationic species, I get that positive charge by removing an electron. So you usually start by removing the electron who has the highest energy. So for example, if I've got sodium, I've got neon S1, so I'm going to remove that one valence electron. If I've got calcium, I've got 2 valence electrons. This is one of the reasons why calcium tends to form this 2+ charge, because it's very nice and stable to have what are called the noble gas configurations. And we're going to go ahead and dive into those reasonings a little bit later. So if I've got an anionic species, I now need to generate a negative charge by adding electrons. And so this is almost always done by adding electrons to a partially occupied subshell. So for example, if I've got chlorine, I've got 1 missing electron in my P subshell. So we'll throw that extra electron in, and we have a nice electron configuration, 3s2, 3p6, which means that you took all those valence electrons and you now made them core electrons by producing an argon electron configuration, which is going to be very stable. You can do something very similar for oxygen. It normally will have a 2p4 configuration. You'll add in 2 electrons there to make 2p6, which now has a noble gas configuration. So in general, we tend to find that elements want to have a full valence shell, whether that means you lose electrons or gain electrons. However, there's one case where that gets a little bit trickier, and that's metals. Because it turns out your transition metals, you'd have to gain a whole bunch of electrons or lose a whole bunch of electrons to generate these nice noble gas configurations. So they tend to shoot for a different ending point. So in these cases, it turns out it's going to be a lot easier for transition metals to lose electrons than gain electrons. So transition metals are almost always going to form cations. And it turns out they do so not by losing electrons from the higher energy 3D or subshell, but from the slightly lower energy 4s. Now, the reason why this happens is because remember, those s and d orbitals are very similar in energy. But it turns out, if you remember back to the structure of your s and d orbitals, your 4s orbital is much bigger than your 3d orbital. So go ahead and try and think of the electrons as being members at a kind of a rowdy concert. If you're going to call the cops and they're going to bust in this concert, are they going to remove people from the cheap seats in the mosh pit or the slightly more expensive seats on the outside? They're going to pull the people from the outside because they're the easiest to grab. And that's more or less what you have happen with your transition metals. So zinc tends to form a zinc 2+ charge, because in this case, you have a full s and d subshell, but it's a little easier to pull those 2 electrons out of that s subshell. Same thing with iron. Iron often forms that iron 2+ charge. So in this case, you end up forming a 3d6 valence valence configuration. So again, in general, it's almost always going to be easier for metal to lose those s electrons because they're much further out. They're easier to grab. You don't have to get into quite so many nuances. And we'll dive into the reasoning behind this in, again, a future lecture. But because it's so much easier to grab those s electrons and the d ones, it turns out that almost all metals tend to form +2 cations. So if you're going to have a metal cation, it's almost always going to have a +2 charge. However, there's a couple notable exceptions. One of the famous ones is that iron tends to adopt an iron 3+ charge. And one of the reasons why is because iron has a configuration that 4s2 3d6. But if you remove 3 electrons, it becomes 3d5. So here's our nice neutral iron. Okay, we've got a full subshell. We've got 6 electrons in our D subshell. Little awkward. But if I remove 3 electrons, I pull those 2 electrons out of the S and 1 out of the D. When I pull that single electron out of the D, ta-da, I now have a 3d5. Now I have that beautiful balanced half-filled D subshell. And this is very energetically favorable. So it's natural for things like iron and ruthenium to adopt this 3d5 configuration or a +3 charge. So this is always going to be a little bit of a slight advantage when you're forming these half-filled subshells. Similarly, for copper, it can form a copper 2+ ion, but it also likes forming a copper 1+ ion. And one of the reasons why is because we start with a 4s1 3d10. If I remove 1 electron, I now have a 3d10 subshell. So I start with this guy, but all I have left is those nice, beautiful D electrons. It's beautiful. And this is going to generate a very natural and stable ionic configuration. So these are going to be the major things to look out for configurations. When looking at transition metals, make note that you get a little bit of oddities when you're essentially, when you can ever generate these half-filled or completely filled D subshells. For ions, try and make sure that you adopt one of these natural configurations. And that for transition metals, it's always easier to remove electrons from the S subshell than the D. Remember these and you'll do fine. Next time, we're going to go ahead and dive into the idea of periodic trends and really looking at ways that different elements will have different properties using what we now know about electron configurations. Until then, take care.